What if everything we believe about the beginning of time is fundamentally incomplete? What if the moment before the Big Bang wasn't empty silence, but something far stranger, something that defies our very comprehension of existence itself? What if nothing isn't actually nothing at all, but rather the most profound and terrifying mystery in all of physics? Tonight, we venture into the dark recesses of cosmological speculation, where the solid ground of observation crumbles and unanswerable questions about pre-universal reality take root. For 13 billion years, humanity has gazed upward at the stars and wondered, where did we come from? But for only the last century have we possessed the mathematical and observational tools to even ask the question properly. And what we've discovered is both humbling and deeply unsettling. The Big Bang isn't the beginning of time itself, since something far stranger. It's the moment when our universe of physics, as we understand its space, time, causality itself, burst into existence from a state so extreme, so beyond our current comprehension, that the very question, what came before, might be physically meaningless. But here's where it gets interesting. Physicists don't actually stop asking that question. Despite official reassurances that asking about before the Big Bang is like asking what's north of the North Pole, brilliant minds continue to probe the edges of our cosmic origin story. They've developed increasingly sophisticated frameworks for thinking about pre-Big Bang physics. And some of their conclusions are genuinely destabilizing. Consider this. Our universe obeys laws. Keen, quantum mechanics governs the subatomic realm. Keen, general relativity governs space-time and gravity. These aren't arbitrary, they're descriptions of how reality works. But where did these laws come from? And more troublingly, did they always exist? Was there a time, or rather, a non-time where different laws prevailed? Or where no laws existed at all? The conventional answer from mainstream cosmology is simple. We cannot know. The Big Bang represents a fundamental boundary. Current physics breaks down at the moment of the Big Bang itself. The universe becomes infinitely dense, infinitely hot, infinitely compressed quantities that our equations describe as singular, which is scientific language for we have no idea what's actually happening here. To ask what came before this boundary is, we're told, to ask a question that has no meaning. Yet this answer satisfies neither philosophers nor physicists, because there's something deeply unsettling about accepting a hard boundary to reality itself. It feels incomplete. It feels like we're missing something crucial about the architecture of existence. So what do cutting-edge theoretical physicists actually propose? Some suggest that the Big Bang wasn't the beginning at all, that our universe is cyclical, part of an infinite series of cosmic deaths and rebirths. Others propose that time itself is emergent, an illusion created by quantum entanglement, which would mean the concept of before the Big Bang is as nonsensical as asking what happened before color. Still others venture into the realm of multiverses, suggesting that our Big Bang was simply one event among countless others, universes spawning from some deeper cosmic substrate that we can barely conceptualize. And here's what troubles many scientists most. We might never be able to test any of these ideas. The pre-Big Bang universe, if it existed, would have left no evidence we can access. No light from that time can reach us. The universe itself might have been smoothed away during the Big Bang's violent birth. We could be asking the most profound questions imaginable about a reality we're fundamentally barred from observing. Yet we keep asking anyway. We keep theorizing. We keep developing mathematical frameworks that probe the boundaries of existence, because that's what consciousness does. It questions. It wonders. It reaches toward the unknowable and tries to make sense of it. What if everything before the Big Bang matters more than we realize? What if the answer to where our laws came from, where our universe came from, where we came from, is hidden in that inaccessible pre-universal realm? What if the greatest truth about reality is precisely the one we're least equipped to uncover? Tonight, we explore these questions not with certainty, but with intellectual honesty about what we actually know, what we speculate, and what might forever remain beyond our grasp. We venture into pre-Big Bang cosmology, where physics dissolves into philosophy and the nature of existence itself becomes the central question. Let's begin! Before we dive deeper into this truly unprecedented exploration of cosmic origins and the mind-bending question of what, if anything, might have existed before time itself, I want to invite you into our community. If you're fascinated by cosmology, theoretical physics, and the deepest mysteries of existence, make sure to hit that subscribe button and ring the notification bell so you don't miss our deep dives into these cosmic questions. Drop a comment below telling me what time it is where you're watching from and where you're located. I absolutely love seeing our global community come together to explore these fundamental questions about reality, consciousness, and our place in the universe. There's something profound about viewers from every continent pondering the same cosmic mysteries simultaneously. We're all staring at the same stars, asking the same unanswerable questions. And if you appreciate the research that goes into these extended explorations, the interviews with physicists, the deep analysis of the latest cosmological papers, the synthesis of complex theories into something comprehensibly like really helps the channel grow and reach more curious minds who wonder about these things. Your engagement literally helps us create more content like this. Now, let's continue our journey into the hidden truth about nothing before the Big Bang, where we'll move from concrete observations to increasingly speculative territory, but always maintaining intellectual honesty about what's established science and what remains profound mystery. The universe is about to get a lot more strange. The question of what existed before the Big Bang represents more than mere academic curiosity, strikes at the very heart of how we understand causality, logic, and the nature of existence itself. For over a century, physicists have reassured the general public with a deceptively simple answer. Nothing came before the Big Bang because time itself began with the Big Bang. Therefore, the question of what came before is fundamentally malformed, like asking what's north of the North Pole. This reassurance is officially and conventionally the correct answer. Fuck Big Bang Theory. As confirmed by decades of observation from Edwin Hubble's 1929 discovery that the universe is expanding, to the detection of the cosmic microwave background radiation in 1965, to modern observations from the James Webb Space Telescope's humanity's most robust description of cosmic origins, the evidence is overwhelming. The theory works. But here's what troubles many physicists. Reassurance often masks incompleteness rather than true understanding. The Big Bang, as described by Einstein's field equations combined with quantum mechanics, represents what physicists call a singularity, a point where the equations produce infinite quantities. The temperature becomes infinite. The density becomes infinite. The curvature of space-time becomes infinite. These infinities aren't signs of precision. They're warning lights indicating that our theories have reached their limits. They're physics saying, I don't know what's actually happening here. The official position from the cosmological establishment is clear and unified. The question of what came before the Big Bang is unanswerable, not because it's difficult, but because it violates the fundamental nature of reality. Time, according to general relativity, is not a separate backdrop against which the universe evolves. Time is woven into the fabric of the universe itself, inseparable from space. When the universe began, time began. To ask what happened before the Big Bang is as confused as asking which direction is south from the South Pole. It's not that we don't know the answer. The question itself is categorically malformed. The safety reassurance here is significant. We don't need to worry that the Big Bang might have been caused by something external, something chaotic, something unknowable. Our universe operates according to the laws of physics as we understand them. These laws appear to be fundamental, elegant, and mathematical. They predict a universe that expanded from an extraordinarily hot, dense state approximately 13.8 billion years ago. The universe we observe matches this prediction with remarkable precision. Yet, despite these reassuring facts, what shadows might lurk in the gaps between what we know and what we assume? This is where the real story begins. Because not every physicist accepts the meaningless question answer. Some of the most sophisticated minds in theoretical cosmology, people who work at Princeton, Stanford, Cambridge, MIT, continue to ask the forbidden question. They've developed elaborate mathematical frameworks for thinking about pre-Big Bang physics. They've published peer-reviewed papers. They've created research programs dedicated to answering the unanswerable. Why would they do this if the question is truly meaningless? The answer is that the conventional answer might be premature. There's a difference between saying our current theories can't address this and saying the question has no meaning. Physics has a history of boundaries that seemed permanent until they weren't. The barrier between matter and energy turned out to be conventionally equals mc. The separation between space and time turned out to be a human perception. They're actually space-time. The boundary between quantum mechanics and gravity remained insurmountable for 80 years until new frameworks like quantum cosmology began bridging the gap. Could the barrier between before the Big Bang and meaningless question also be conventional? This tension between official reassurance and active scientific exploration defines the landscape of pre-Big Bang cosmology. We have a consensus answer. We also have active, rigorous research suggesting that answer might be incomplete And the more we learn about the quantum nature of gravity, the structure of space-time itself, and the mathematics of extreme conditions, the more the question begins to seem less like a philosophical error and more like a genuine frontier of physics. So here's what we know with certainty. The Big Bang happened. The universe expanded from an incredibly hot, dense state. The laws of physics, as we understand them, describe this process with impressive accuracy. Everything we observe aligns with this picture. But what happened at the very moment of the Big Bang? What happened infinitesimally before? What set the initial conditions that allowed our universe to exist? These questions remain genuinely open. They remain genuinely profound. And the physicists asking them are not fringe thinkers there among the most rigorous minds currently working in theoretical physics. Despite these reassuring facts, despite our confidence in the Big Bang theory, despite the elegant simplicity of saying time began with the universe, there remains an abyss beneath our feet. An abyss we're increasingly sophisticated enough to peer into, but not yet wise enough to fully understand. That abyss is the subject of tonight's exploration. To understand what physicists mean when they talk about the Big Bang, we need to confront the sheer extremeness of the initial conditions. These aren't just big numbers. They're numbers so extreme they exceed human intuition entirely. They're numbers that would make any physical system we've ever encountered seem quaint by comparison. Let's start with temperature. At the moment of the Big Bang, or rather, 1 Planck time after the Big Bang, about y-43 seconds, which is the earliest moment our physics can meaningfully describe the temperature of the universe, was 1032 Kelvin. That's a 1 followed by 32 zeros. To give you scale, the center of the sun is about 15 million Kelvin. A supernova core reaches billions of Kelvin. The most extreme conditions physicists can create in particle accelerators reach trillions of Kelvin. The early Big Bang universe was a trillion times hotter than that. It's not just hotter, it's incomprehensibly hotter. The gap between our intuition and this number is absolute. At that temperature, all particles would be moving at nearly the speed of light, 186,000 miles per second. That's fast enough to circle the Earth 7 times in a single second. Yet every particle in the primordial universe was moving at roughly that speed, constantly colliding with every other particle at unimaginable energies. Now consider density. The entire observable universe containing more stars than there are grains of sand on every beach on Earth, existing across billions of light years, was compressed into a space smaller than an atom, smaller than an atomic nucleus, smaller than anything we can actually imagine. The density was so extreme that the distinction between matter and energy became meaningless. It's not that matter was packed tightly, it's that matter and energy were the same thing, vibrating at the boundary between existence and non-existence. The pressure would have been incomprehensible. Using the ideal gas law, the pressure in the early universe would have been approximately 10,113 pascals. For comparison, the pressure at the center of Jupiter is about yp pascals. The pressure deep within the Earth is about ya pascals. The early Big Bang universe was a million, billion times more pressurized than anything we've ever measured. It's not possible for matter to exist under such conditions, or rather, the concept of matter becomes meaningless at such extremes. Here's what makes this relevant to our question about pre-Big Bang physics. At these extremes, physics itself breaks down. General relativity and quantum mechanics give incompatible answers. General relativity, Einstein's theory of gravity, suggests that the density becomes infinite. That space-time itself becomes infinitely curved, that the universe becomes a single point. Quantum mechanics, the physics governing the subatomic realms, suggests that matter and energy fluctuate wildly at tiny scales, that nothing can ever be precisely defined, that uncertainty is built into reality at the deepest level. These two theories cannot both be completely right at the moment of the Big Bang. Something must give. Something must give way. And that's the profound source of the mystery. One way to think about it, imagine trying to describe the behavior of water using only the laws of fluid mechanics. At everyday scales, this works perfectly. Water flows, splashes, forms waves, but at the atomic scale, fluid mechanics breaks down. Water is made of discrete molecules bouncing around. You need quantum mechanics to understand what's actually happening. Similarly, gravity seems smooth and continuous at everyday scales described perfectly by Einstein's space-time geometry. But at the quantum scale, at the Planck scale, about 10 to 35 meters, gravity itself must become quantized. It must become discrete, probabilistic, uncertain. The Planck scale is where the early Big Bang universe lived. It's a realm so far beyond our experimental capability that we may never directly observe it. Yet this is precisely the realm where the question what came before becomes interesting. Because at this scale, time itself might have a different nature than we assume. Consider this. Quantum mechanics says that energy and time are complementary quantities related by Heisenberg's uncertainty principle. You cannot know both a particle's energy and the moment at which you measured that energy with perfect precision. The more precisely you know the energy, the less precisely you can know the time. In the early Big Bang universe, the energy density was so extreme that the uncertainty in time itself might have been enormous. The concept of a moment might have been spread out. Time itself might have been blurred. Is it possible that at the moment of the Big Bang, time became so uncertain, so quantum in nature, that the very concept of before and after becomes meaningless? Not because the question is philosophically confused, but because time itself emerges as a classical, continuous quantity only after the universe cools slightly. Is time an illusion created by the decoherence of quantum systems? A pattern that emerges from the entanglement of particles as the universe expands and cools. These aren't fringe questions. These are serious proposals by serious physicists, and they're motivated directly by the extreme conditions at the Big Bang. The numbers that staggered the infinities that emerge in our equations aren't failures of the theory. They're signals. They're the universe telling us, you don't have the right framework for this. Your equations break down here. Something different happens. And what that something might be what physics lurks at the Planck scale. what time actually is, whether before has meaning remains among the most profound open questions in all of science. But what if these infinities hide something more profound still? What if they're not just signs of theoretical inadequacy, but indicators of something almost incomprehensible, something about the fundamental nature of existence itself? If we're going to peer into pre-Big Bang physics, we need to understand what evidence we actually have about the Big Bang itself. And the most remarkable evidence comes from something unexpected, a whisper of radiation filling the entire universe. Afterglow from the moment when the universe became transparent. In 1965, Arno Penzias and Robert Wilson discovered something by accident. They were working with a radio antenna at Bell Labs, trying to detect faint signals from space. Instead, they found a constant hiss static that came equally from all directions, with almost perfect uniformity. The noise was everywhere, coming from every part of the sky. They initially thought it might be pigeon droppings on their antenna. After ruling that out, they realized they detected something far more profound. The cosmic microwave background, CMB, the oldest light in the universe. This is background radiation that has been traveling toward us since the universe was only 380,000 years old, when it was still a hot plasma opaque to light. Before that moment, the universe was so hot and dense that photons, particles of light, couldn't travel without being instantly absorbed by charged particles. It was completely opaque, like being inside a thick fog. But as the universe expanded and cooled, the fog lifted. Neutral atoms formed. Light could finally travel freely. And we're still detecting that light today, aged and redshifted by 13.8 billion years of cosmic expansion. What makes the CMB remarkable is its uniformity. It's almost perfectly smooth when we measure its temperature across the entire sky. It's consistently 2.725 Kelvin, about minus 454 degrees Fahrenheit. But here's the crucial part. It's not perfectly uniform. There are tiny temperature variations, differences of less than 1 part in 100,000. These tiny ripples, discovered in detail by the COBE satellite in 1992 and mapped precisely by WMAP and Planck satellites, represent the density fluctuations in the early universe. And this is where it gets interesting. These density fluctuations appear to match predictions from cosmic inflation theory. Cosmic inflation is a modification to the Big Bang theory proposed independently by Alan Guth and Andre Linde in the 1980s. According to inflation, immediately after the Big Bang, during the first fraction of a second, the universe didn't just expand. It exploded. It underwent exponential expansion, doubling in size repeatedly, driven by an enormous energy field called the inflaton field. In a fraction of a second, a region smaller than a proton inflated to cosmic scales. Inflation solves several mysteries that the original Big Bang theory couldn't explain. It explains why the universe is so uniform because, in the inflationary picture, our entire observable universe expanded from a tiny, causally connected region that had time to reach the same temperature. It explains why space appears so flat, the same way inflating a balloon makes a tiny region appear flat. and it predicts the exact pattern of density fluctuations we observe in the CMB. This unprecedented matching between predictions and observations made inflation the dominant theory in cosmology by the 1990s, and most physicists consider it essentially confirmed by the extraordinary precision of CMB measurements. But here's what makes inflation deeply relevant to pre-Big Bang questions. Inflation doesn't actually solve the problem of the beginning. It just pushes it backward. Instead of asking what caused the Big Bang, we now ask what caused inflation? What triggered it? What set the initial conditions for the inflattened field to exist? In 2003, Russian physicist Andrei Lind proposed something radical: eternal inflation. His mathematical analysis suggested that once inflation begins, it might never completely stop. Instead, the universe continuously spawns new inflating regions, which spawn more regions, creating a fractal structure of expanding universes. In this picture, our Big Bang isn't the beginning of everything, it's just one bubble in an infinite cosmic foam. But eternal inflation opens a door that seems to lead somewhere even stranger. If inflation is eternal, if new universes continuously spawn from existing ones, then there must be a substrate, something underlying all of this, something that was there before the first inflation began, something that had to exist in order for anything to exist. This chemical signature of eternal inflation, the mathematical structure underlying infinite cosmic reproduction, opens doors to speculation that we're only beginning to explore. Because if eternal inflation is correct, if universes breed universes in some deeper space-time, then the question what came before the Big Bang transforms into what is the nature of the space, the metaspace, the substrate that allows universes to exist within it. The CMB anomalies support this speculation. When we look at the highest resolution CMB maps from the Planck satellite, we find unexpected patterns, cold spots, unexpected correlations between regions of the sky that shouldn't be correlated according to standard inflation theory. Some researchers have proposed that these anomalies might be signatures of collisions with other universes, evidence that our Big Bang wasn't isolated, but one event among many in a multi-universal cosmos. Other physicists argue these anomalies are statistical flukes, nothing more. The debate continues. But the fact that we can even ask these questions, that we have data precise enough to test these exotic hypotheses, represents a profound shift. The CMB, that whisper of ancient light, has become a window into pre-Big Bang cosmology. This physical signature opens doors to speculation that the universe we inhabit is far stranger than we imagined, that our Big Bang might be one explosion among countless others, that what we call nothing before the Big Bang might actually be an infinite landscape of quantum possibilities, cosmic multiverse where universes are born continuously from a substrate so alien to our experience that we lack even the language to describe it. Before we venture further into speculative territory, we need to directly address a fundamental question. Is there any physical danger implied by the fact that we don't fully understand pre-Big Bang physics? The answer is unequivocally no. Let me be clear and specific about this. First, whatever happened before the Big Bang, if That phrase even has meanings completely separated from our present reality by 13.8 billion years of cosmic evolution. The initial conditions of the Big Bang, whatever they might have been, are now encoded in the current state of the universe. We can observe that current state. We can measure it. We can test our theories against those measurements. And our theories work remarkably well. The Big Bang theory, combined with cosmic inflation, predicts with astonishing precision the abundance of hydrogen, helium, and lithium in the universe tested against observations. The spectrum and intensity of the cosmic microwave background tested against satellite data. The distribution of galaxies across cosmic scales tested against surveys. The accelerating expansion of the universe confirmed by supernova observations in 1998. These predictions match observations to better than 1 part in 1,000 in many cases. This level of agreement doesn't happen by accident. Our understanding of the Big Bang and the subsequent cosmic history is fundamentally sound. Moreover, the physics of the early Big Bang, even the extreme conditions we described as mathematically contained, it doesn't lead to paradoxes or contradictions in our current universe. The physical processes that occurred 13.8 billion years ago have been resolved by time. The universe has settled into its current, stable state. There is no cascade of effects from pre-Big Bang physics that threatens our reality today. To be more specific, could the universe collapse? Could another Big Bang occur? Could we be destroyed by forces lurking in pre-universal physics? These questions have precise answers from general relativity. Whether the universe will collapse depends on the density of matter and energy in the universe. Current measurements, particularly from supernova observations, indicate the universe is accelerating in its expansion. The density appears to be below the critical density needed for eventual collapse. The universe will likely expand forever, becoming progressively colder and emptier. There is no physical threat from cosmic collapse. Could we be destroyed by forces from outside the universe? This question is physically incoherent. Our universe is, by definition, the totality of all space, time, matter, and energy accessible to us. If something existed outside it and could affect us, it would be part of our universe by definition. The very concept of force implies causality, which is built into space-time itself. If pre-Big Bang physics exists in some other domain, it operates under potentially different rules. Those rules, whatever they are, don't extend into our universe. We are protected by the boundary of the Big Bang itself. Could quantum fluctuations create dangers we haven't anticipated? Could vacuum decay, a hypothetical transition of the quantum field that underlies space-time to a lower energy state, be triggered by pre-Big Bang physics? The answer to both is no, based on our current understanding. Quantum fluctuations in the early universe are now understood through quantum field theory. They create density perturbations that grow into galaxies, a well-studied and safe process. Vacuum decay is theoretically possible, but it would be a universal phenomenon, unrelated to pre-Big Bang physics, and if it hasn't happened in 13.8 billion years, it's extraordinarily unlikely to happen. There's no mechanism by which pre-Big Bang physics would trigger it. The most important point, The fact that a question is scientifically interesting, doesn't make it a practical threat. Scientists wonder about black hole interiors, the fate of Hawking radiation, the behavior of matter at the Planck scale, the quantum nature of consciousness. These are profound intellectual questions. They don't pose dangers to human civilization. They're wonderings about how reality works, not indications that reality is about to break. This bears repeating. Because it's crucial, our understanding of the Big Bang is based on overwhelming observational evidence. The universe expands. It was hotter and denser in the past. The CMB exists as predicted. These aren't speculations, they're facts. Whatever comes next in our understanding, whatever theory supersedes the Big Bang in the 22nd century, will likely encompass these facts rather than overturn them. The worst-case scenario, some might imagine that physicists are missing. Something catastrophically wrong about reality's foundation is not credible given the evidence. We've tested our theories with extraordinary precision. We've found no contradictions with observations. We've made predictions that proved correct. This is how science works. This is how knowledge advances. But this doesn't mean all questions are answered. It doesn't mean we've discovered the complete nature of reality. It means we've found a robust description of how the universe has behaved for 13.8 billion years. Whether that description extends to pre-Big Bang physics, what physics governs the moment of the Big Bang itself, what the ultimate origin of the universe might be, these remain open questions. Profound open questions, yes. Practically dangerous, no. So we can set aside fear. We can move forward into speculation not from a place of dread, but from a place of intellectual curiosity. The safety of our physical reality is secure. Our danger is only to our current understanding the danger of discovering that we were wrong. That reality is stranger than we imagined. That the universe operates according to principles we've barely begun to grasp. And that danger, the danger of being wrong, the danger of transformation through knowledge, is precisely the danger that drives all science. It's time to venture into that danger. Now that we've established that pre-Big Bang physics poses no practical threat to our current reality, we can ask the more interesting question: what might the mathematics of pre-Big Bang physics look like? Here we enter explicitly speculative territory. I want to be absolutely clear. What follows is not established science. It's not even consensus speculation. It's the frontier of what some very brilliant theoretical physicists are currently exploring. Some of these ideas will be wrong, probably will be. But they represent the cutting edge of how we think about cosmic origins. Let's start with Hartle-Hawking no-boundary proposal, developed by James Hartle and Stephen Hawking in 1983. Their central insight was profound. What if time is not fundamental? What if time is an emergent property, a way that our minds organize the universe rather than a feature of the universe itself? In their formulation, they used a mathematical technique called path integral formulation of quantum mechanics. In this approach, instead of thinking of the universe as having a definite history that unfolds through time, we think of it as a superposition of all possible histories. The universe isn't marching down a single timeline. It's existing in all possible ways simultaneously. Now here's the key. Hartle and Hawking imagined that space-time itself is finite but without boundaries. Imagine the surface of a sphere. If you travel in any direction, you eventually return to where you started, but the sphere has no edge, no boundary. It's no place where reality ends. Space-time might be similar, they proposed. It might be a four-dimensional, curved surface with no boundary, extending infinitely inward, but not outward. It has a beginning in the sense that near the Big Bang, space-time becomes more like a sphere's north pole, where the concept of before dissolves. In this picture, the question what came before the Big Bang evaporates. There is no before because the beginning is not a temporal event but a geometric feature of space-time itself. It's like asking what's north of the North Pole. The question is meaningless because the geometry doesn't extend in that direction. Hawking found this proposal beautiful precisely because it eliminates the problem. No boundary. No need for initial conditions imposed by some external creator or quantum fluctuation. Just geometry, the elegant mathematical structure of space-time. With no beginning or end, just a curved surface where time itself emerges. But this is crucial. Other physicists found problems with this proposal. Araja Penrose, a physicist of equal stature to Hawking, argued that the no-boundary proposal assumes the wrong mathematics. He proposed instead conformal cyclic cosmology, CCC, a radically different vision. In Penrose's vision, the universe doesn't have a beginning. Instead, it's eternal and infinite, but infinities fold upon themselves. What we call the Big Bang is actually the infinite future of a previous universe, infinitely redshifted. And our infinite future becomes the Big Bang of the next universe. The universe is an eternal sequence of eons, each looking like a full Big Bang and expansion, but actually connected to the previous one through a mathematical transformation called a conformal rescaling. The profound implication: there is no before the Big Bang, because the Big Bang is actually the final moment of the previous universe. Time doesn't begin, it's eternal. What we perceive as the beginning is just a junction between eons. Penrose has developed this idea into a research program spanning decades. He's proposed ways to test it using observations of the CMB. He argues that evidence of collisions between universes might be visible as concentric circles in the background radiation. Some researchers have claimed to find such circles. Others argue they're statistical artifacts. Then there's eternal inflation, already mentioned but worth deeper exploration. Andre Lind and others developed the idea that inflation, that rapid expansion in the first fraction of a second, might not end cleanly. Instead, different regions of space can end inflation at different times. This creates pocket universes, separate regions with potentially different physical laws. And crucially, as regions finish inflating, they spawn new regions that continue inflating. This process can continue eternally. The implication: our Big Bang wasn't the first inflating region. Inflation has been going on forever, spawning infinite universes. Our universe is one bubble in an infinite cosmic foam. And there's a metaverse, a deeper level of reality where this foam exists. But what's the nature of that deeper reality? That's where speculation becomes truly exotic. Some physicists propose that the metaverse might be a quantum vacuumous state without conventional space or time, where quantum fluctuations continuously spawn new bubbles of inflating space-time. Others propose that it might be governed by some deeper set of physical laws. Laws we can't deduce from observing our universe alone. Richard Gott has proposed a closed time-like curve interpretation of quantum cosmology, the possibility that the universe might be a loop in time, where the future loops back to the past, creating a bootstrap universe that creates itself. A universe with no external cause, because causality loops back on itself. Then there's the idea that consciousness might play a role, the participatory anthropic principle proposed by John Wheeler. If observation creates reality at the quantum level, did the universe require conscious observers to come into existence? Did consciousness somehow reach backward in time through quantum entanglement to create the initial conditions for its own existence? This sounds like science fiction, and it is. But Wheeler was one of the greatest physicists of the 20th century. He wasn't being whimsical. He was pointing to genuine mysteries in the mathematics of quantum mechanics. And then there are the truly exotic proposals: the universe as a simulation, as a holographic projection, as a side effect of higher dimensional space-time, as one possibility among a quantum superposition of all possible universes, each with different physical laws. Some of these ideas are more rigorous than others. Some rely on speculation beyond the current experimental reach. But they're all attempts by sophisticated physicists to answer a genuine mystery. Where did our universe come from? What they share is a common theme. The boundary between before and after the Big Bang might be far more subtle than we initially assumed. Time might not be fundamental. Space might emerge from more basic quantum structures. The initial conditions of our universe might be connected to previous universes or determined by deeper mathematics we haven't yet discovered. This bears repeating. These are speculations. But they're the speculations of people who understand the mathematics of general relativity and quantum mechanics at the deepest level. They're not guesses. They're informed explorations of the boundaries of our theories. Let's venture further into the most dramatic of these speculations. Here's where we step fully into speculative territory and construct the most mind-bending possibility that emerges from contemporary physics. What if the entire universe is a quantum fluctuation arising spontaneously from absolute nothingness? This isn't new. The physicist Lawrence Krauss has popularized the idea, and it has roots going back to John Wheeler's work in the 1960s, but the full implications are rarely explored. Let me build this carefully. Start with quantum mechanics. In quantum mechanics, nothing truly nothing, not even empty spaces unstable. This is a consequence of Heisenberg's uncertainty principle. The uncertainty principle says that certain pairs of properties cannot both be precisely known. Energy and time are paired. The more precisely you know the energy of a system, the less precisely you can know the moment you measured it. Now, if nothing exists, Civ, there is literally no energy. No space, no time, no universe. This violates the uncertainty principle. You would have perfect knowledge of the energy, it's zero, and perfect knowledge of the time, it's undefined. there is no time in nothing. According to the uncertainty principle, this is impossible. Nothing cannot exist. Therefore, using the logic of quantum mechanics, something must exist, not because of any external cause, but because absolute nothingness is excluded by the laws of quantum mechanics. But that something doesn't have to be our universe. It could be a quantum fluctuation, a temporary violation of energy conservation where particle-antiparticle pairs spontaneously appear and annihilate, occurring in the nothingness because the nothingness is unstable to such fluctuations. Now, here's the exotic part. What if one of these quantum fluctuations, instead of immediately annihilating, expanded? What if the inflation field emerged from quantum vacuum fluctuations, and by pure chance entered the inflationary regime where exponential expansion becomes self-sustaining? In this picture, the universe literally creates itself from nothing. Not from a pre-existing quantum vacuum. There is no pre-existing anything. From the mathematical vacuum, the nothingness that is required by quantum mechanics to be unstable. Lawrence Krauss has drawn criticism for popularizing this idea without sufficient precision. Philosophers, and even some physicists, point out that quantum vacuum isn't truly nothing. It's a mathematical structure governed by laws, and those laws might require explanation. So this doesn't fully answer the question of ultimate origin. It just pushes it back one step. Instead of asking, why does the universe exist, we ask, why do the laws of quantum mechanics exist? But here's where it becomes genuinely speculative and genuinely profound. What if the laws of quantum mechanics are themselves emergent? What if even more fundamental a truth so deep it transcends reality itself is that nothingness is unstable? That mathematics, in some ultimate sense, cannot avoid creating something. That quantum mechanics, our space-time, our physical laws, are not arbitrary but inevitable consequences of the fact that absolute nothingness is a contradiction. In this vision, there is no before the Big Bang, not because time is emergent, but because nothing contains within itself the inevitability of something. The universe doesn't come from nowhere. It comes from the absence of nowhere, from a logical impossibility that forces reality into existence. Take this even further. If the universe spontaneously creates itself from nothing through quantum fluctuations, then mathematically, all possible universes might simultaneously exist. Every possible configuration of quantum fields, every possible set of physical laws, every possible universe that can be described by any mathematical structure. This is the many worlds interpretation taken to its logical extreme. Not just quantum superpositions existing in parallel, but all possible universes existing in parallel, each one equally real, each one emerging spontaneously from the quantum vacuum. In this vision, and again, emphasizing this is wild speculation grounded in real physics, we don't ask why our universe exists, or why it has the laws it does. Instead, we recognize that it must exist along with all other possible universes. As a necessary consequence of the logical impossibility of absolute nothingness, this raises profound questions about causality. If all possible universes exist, then our universe wasn't caused by anything. It wasn't selected for. It's not special. It's simply one member of an infinite ensemble of possibilities, all equally necessary, all equally real. But if all possible universes exist, how do we exist within one specific universe with specific physical laws? Here's where quantum mechanics provides a startling answer: because we must. A universe with no conscious observers is, in a sense, unobserved. In quantum mechanics, unobserved systems exist in superposition in all possible states simultaneously. A conscious observer forces the system into one definite state through the act of measurement. This is where the participatory anthropic principle returns. Perhaps the universe requires observers to collapse its quantum state, and observers require a universe fine-tuned to produce them. This creates a self-consistent loop. The universe exists in a quantum superposition of all possibilities. Conscious observers emerge in some of those possibilities. When they observe, they collapse the superposition, forcing reality to match one of the possibilities where observers exist. In other words, we find ourselves in a universe fine-tuned for consciousness, not because the universe was designed or because we're infinitely lucky, but because we can only ever observe ourselves in a universe that produced us. This is the weak anthropic principle, and it's a genuine principle in physics, not mysticism. But then comes the radical extension: if all possible universes exist, and conscious observers only exist in universes with consciousness-producing physical laws, then from our perspective, we will always find ourselves in such a universe. We will always find the laws fine-tuned for our existence, not because of causality or design, but because the only possible universes available for us to observe are those in which we exist. Taken to its logical extreme, the universe must exist, must be quantum mechanical, must produce consciousness, must have observers, because the absence of these things is logically impossible given the initial condition of absolute nothingness. There is no before because before is meaningless. Before implies time. Time is emergent. Emergence requires a substrate. That substrate requires laws. Those laws require a logical foundation. That foundation is, nothing is unstable. Everything we see, stars, galaxies, consciousness, meaning, ourselves, emerges inevitably, necessarily, from the simple fact that absolute nothingness contradicts itself. This is speculation. Deep, profound, grounded in real physics but stretching far beyond observational evidence. But it's the kind of speculation that represents the frontier of how cutting-edge physicists think about cosmic origins when they're willing to think radically. The implications are staggering. The worst case Tev-Trivik for our reality, instead, it's Liebrat, ing. It means the universe doesn't need an explanation beyond itself, doesn't require a creator or design, exists with mathematical inevitability. And consciousness, our consciousness is, not a cosmic accident, but an inevitable consequence of reality itself. If the universe we inhabit is merely one bubble in an infinite foam of eternal inflation, then the philosophical landscape transforms entirely. We're forced to confront questions that were once purely philosophical questions about necessity, uniqueness, and the meaning of physical laws themselves. Let's establish the context. Eternal inflation suggests that the universe didn't have a unique Big Bang event. Instead, inflation, that rapid exponential expansion, has been occurring eternally in various regions. Some regions finish inflating and cool to normal expansion. Others continue inflating indefinitely. The result is an infinite multiversal landscape with countless bubble universes, each potentially governed by different physical laws. This resolves a profound problem in physics, the fine-tuning problem. Our universe appears exquisitely fine-tuned for the existence of complex structures and conscious life. The strength of the strong nuclear force, the weak nuclear force, gravity, electromagnetism, these are fundamental constants that determine whether atoms can form, whether stars can burn, whether chemistry can happen, whether life can emerge. Change any of these values by even a few %, and the universe becomes sterile. No atoms, no stars, no life. For decades, physicists were troubled by this. Why are the fundamental constants precisely the values they are? Why is this universe so carefully balanced to produce consciousness? 3 possible answers emerged. First, the universe might be designed. A creator god might have fine-tuned the constants deliberately. This is the theological answer. Second, we might be infinitely lucky. The probability of a universe like ours arising by chance might be infinitesimal. But if you have infinite time and infinite attempts, even infinitesimal probabilities eventually occur. We find ourselves here simply because, by pure statistical improbability, our universe happened to have the right constants. Third, if the multiverse is real, then all possible universes exist. Most are sterile and lifeless. Some, by chance, have the right constants to produce galaxies, stars, chemistry, life, and consciousness. We find ourselves in one of the rare universes that permits our existence not because of design or luck, but because this is the only kind of universe where entities like us can observe the universe. This is the anthropic solution. It's not satisfying to most physicists. It feels like giving up on explaining fine-tuning. If all possible universes exist, then we necessarily find ourselves in one that permits observation. The multiverse framework also addresses another problem. What sets the initial conditions of the universe? In classical physics, you need boundary conditions to solve the equations. The Big Bang theory doesn't explain what set the temperature, density, and expansion rate at the moment of the Big Bang. It just assumes initial conditions and predicts what happens afterward. But if eternal inflation is correct, the initial conditions for any specific universe, our universe, are determined by quantum fluctuations in the pre-Big Bang meta-universe. Quantum mechanics shows that any initial state is probabilistically accessible through quantum tunneling. So the question, why these initial conditions, has a quantum mechanical answer. Because quantum mechanics allows any initial conditions to arise with some probability. This raises a deeper question. Does the multiverse framework actually explain anything? Or does it just reframe the problem? Critics argue it does little more than reframe. Instead of asking, why does our universe have these laws, We ask, why does the meta-universe that produces universes have these laws? We've pushed the explanation back another level without fully solving the underlying mystery. But proponents argue this is how science progresses. Newton's laws didn't explain gravity. They described it. Einstein's relativity deepened that description, but didn't fully explain why gravity exists. Perhaps quantum field theory underlying the multiverse is simply a deeper description, not an ultimate explanation. Here's what makes the multiverse relevant to pre-Big Bang physics. If true, it suggests that before the Big Bang is meaningless in a specific, profound way. Not because time is relative, or because causality loops, but because there is no before. The Big Bang is the beginning of our observable universe specifically. But the universe capital U is the infinite ensemble of all possible universes. And that ensemble might be eternal. The deeper question becomes, what gives rise to the multiverse itself? What physics governs the meta-universe where all these bubbles spawn? This is where speculation truly becomes wild. Some physicists propose that the multiverse might be self-creating, bootstrap structure, where universes spawn other universes in an eternal network with no beginning. Others suggest the multiverse might be a specific solution to some deeper theory of quantum gravity we haven't yet discovered. Still, others propose that the multiverse might itself be one of many meta-multiverses in an infinite regress of levels. The cosmologist Max Tegmark has proposed a taxonomy of multiverses. Level 1. Multiple regions of space that are causally disconnected from us, each with the same physical laws but different initial conditions. This follows directly from eternal inflation. Level 2. Regions with different physical laws, arising from different values of quantum fields at the beginning of each bubble. This requires eternal inflation plus a mechanism for law variation. Level 3. The many worlds interpretation of quantum mechanics, where all possible outcomes of quantum measurements occur in separate branches of reality. Level 4. All mathematically consistent universes exist with equal reality. Every logically possible universe, whether arising from eternal inflation or not. Each level is progressively more speculative, and each represents a potential answer to the pre-Big Bang question. They're not mutually exclusive. The actual multiverse might incorporate elements of each framework. The implications raise questions that hover between physics and philosophy. If all possible universes exist, does moral relativism follow? If there's a universe where the Nazis won and another where they lost, are both equally real and morally equivalent? Most physicists would say no moral frameworks exist within universes. The multiverse doesn't dissolve moral responsibility. But the philosophical implications are unsettling. If our universe is one among infinite others, does meaning collapse? Does the vastness eliminate the significance of individual consciousness, individual choices, individual lives? Some find the multiverse philosophically disturbing for exactly this reason. Others find it liberating our universe exists. Therefore, we exist. Therefore, our choices matter within our universe. This raises profound questions about what exists means. Does mathematical consistency equal existence? If I can write down the equations describing a universe, does that universe actually exist? Most physicists would say yes, following the mathematical universe hypothesis. But this transforms the nature of reality. We're no longer asking why the universe exists. We're asking why anything is real, including abstract mathematical structures. And the answer, increasingly, seems to be because existence and mathematical consistency are the same thing. The cosmic context, then, transforms pre-Big Bang speculation. The Big Bang wasn't a beginning, it was a transition. Our universe wasn't created, it was selected probabilistically from the multiverse. Physical laws aren't mysterious accidents. They're inevitable consequences of the mathematical universe. And the universe before the Big Bang, if before, has meaning at all might be the infinite quantum foam that is the multiverse itself, eternally spawning universes without beginning or end. We've journeyed deep into speculation. And now we reach a question so fundamental that we've nearly transcended physics entirely and entered pure philosophy. But it's a question that increasingly occupies serious physicists. Does anything precede mathematics itself? Or is mathematics the ultimate foundation? For most of history, mathematics was viewed as a human invention. We created the natural numbers to count. We created geometry to measure space. We created calculus to describe motion. These were tools we developed to understand reality, but reality existed independently of our mathematical descriptions. Then something peculiar happened. Mathematics became unreasonably effective. Eugene Wigner called this the unreasonable effectiveness of mathematics in the natural sciences. Physicists would develop mathematical equations to describe phenomena. Those equations would make predictions. And when tested, those predictions would be correct with extraordinary precision. It seemed almost impossible that our invented mathematical structures would align so perfectly with physical reality. How could abstract human constructs align with nature so precisely? One possible answer: mathematics isn't invented, it's discovered. Numbers, geometric relationships, algebraic structures exist in a Platonic realm of abstract forms. Minds access this realm and translate what we find into our mathematical notation. In this view, mathematical truths are eternal, universal, and independent of physical reality. 2 + 2 = 4 doesn't depend on the existence of the universe. This relationship would be true even if no conscious beings existed to calculate it. But here's the radical implication. If mathematical truths are eternal and universal, and physical laws are fundamentally mathematical, then physical laws are also eternal and universal. They don't require creation or explanation. They simply must be. The mathematical universe hypothesis, proposed by physicist Max Tegmark, takes this to its logical extreme. Physical reality is a mathematical structure. Not that mathematics describes reality. Reality is mathematics. Electrons aren't made of anything deeper than mathematics. They're patterns in abstract mathematical structures. Galaxies aren't made of anything. They're configurations of equations. Consciousness isn't made of anything. It's the information processing within mathematical systems that reach a certain complexity. If this is true, then the question what came before the Big Bang transforms. The Big Bang isn't the creation of a mathematical structure. It's the emergence of a specific mathematical structure from the infinite landscape of all possible mathematical structures. And there's no before, because before requires time, and time is part of the mathematical structure. The structure exists in a timeless sense, like how a geometric shape exists in a timeless, non-physical way. All moments of the universe, past, present, future, exist simultaneously within the mathematical structure. This dissolves the pre-Big Bang question entirely, but in a way that raises a deeper mystery. Why does the mathematical universe hypothesis work? Why can physical reality be reduced to mathematics? Why is mathematics so effective? Tegmark's answer is simple and staggering, because if it weren't, we wouldn't observe it. We're conscious observers, and consciousness emerges only in mathematical structures that evolve into conscious beings. Therefore, we necessarily find ourselves in a universe that is mathematical, because that's the only kind of universe that could produce us. This brings us back to the anthropic principle, now in its deepest form. We don't observe the mathematical universe because it was designed. We observe it because it's a tautology. The universe we observe must be one that produces observers. And observers can only emerge in mathematically consistent universes. Therefore, we necessarily observe a mathematically consistent universe. The implication: there is no need to explain why mathematics works. There is no deeper foundation beneath mathematics. Mathematical consistency is the foundation. Reality is mathematics. And consciousness is the mechanism by which mathematical structures observe themselves. But now a truly profound question arises. Why is there a multiverse of all possible mathematical structures? Why does the realm of abstract forms exist? Here we reach the absolute boundary of what physics can address. Physicists who contemplate this question are forced to admit we're asking something beyond science. We're asking why there is something rather than nothing, in a way. That even the existence of all possible mathematical structures is something. Some physicists appeal to a final anthropic argument. If mathematics is the ultimate reality, and mathematics consists of all possible structures, then asking why is incoherent. Why implies causality. Causality implies time. Time is part of specific mathematical structures. The metal of existence of all possible mathematical structures cannot be explained in terms of causality. Because causality is internal to structures. In other words, asking why mathematics exists is like asking why existence exists. You're asking the question with tools that only work within existence. The question dissolves. Other physicists find this unsatisfying. They note that the mathematical universe hypothesis is itself speculative and potentially untestable. We might be wrong about all of this. Reality might not be fundamentally mathematical. There might be a deeper layer beneath mathematics. But if there is, we have no framework even to speculate about its nature. Our best theories are mathematical. Our only tools are mathematical. if there's something deeper than mathematics, our minds might be categorically incapable of understanding it. This raises a humbling realization. There might be fundamental questions about reality that consciousness cannot answer. Not because they're too difficult, but because consciousness itself emerges from mathematics. A mathematical entity cannot fully understand the non-mathematical foundation from which it emerges. Just as a character in a novel cannot fully understand the author who created it. Perhaps the hidden truth about nothing before the Big Bang is that it's fundamentally inaccessible to thought. The pre-Big Bang realm, if it exists, operates according to principles that transcend causality, time, and mathematical structure. Those principles cannot be modeled, described, or even conceptualized within our mathematical framework. In that case, asking about pre-Big Bang physics is like asking what a point has inside it. The question is founded on a category error. Or perhaps the truth is even stranger. Perhaps there is no pre-Big Bang realm. Perhaps the Big Bang truly is the beginning, the moment when mathematical structure first emerges from the groundless ground of pure possibility. The moment when existence becomes conscious of itself through the emergence of observers. In this vision, before the Big Bang, there was nothing, not even mathematics. And the Big Bang is the birth of mathematics itself. The crystallization of one specific mathematical structure from infinite potential. Consciousness, our consciousness is the universe becoming aware of this crystallization. It would mean we're not observing the universe. The universe is observing itself through us. Now that we've ventured deep into pre-Big Bang speculation, let's explore something often overlooked, the institutional and social implications if one of these speculative frameworks turned out to be correct. How would humanity respond to a confirmed discovery that fundamentally changed our understanding of cosmic origins? Let's imagine a specific scenario. Suppose observational evidence emerged that convinced the scientific community that eternal inflation is correct, that the multiverse is real, that our Big Bang wasn't unique but one event in an infinite cascade of universe creation. The immediate impact on institutional science would be profound. Currently, cosmology operates within a framework of a single universe with a single set of physical laws. Scientists search for the mechanisms that determined our universe's initial conditions and physical constants. We try to explain fine-tuning through symmetries, field theories, and accident. The entire field is oriented toward explaining one observed reality. If the multiverse were confirmed, this orientation would shift fundamentally. The relevant question wouldn't be, why do our constants have these values? The answer would be, because we evolved in one of the universes where they do, but rather, what framework governs the multiverse? What meta-laws determine the landscape of possible universes? The institutional structure would change. New journals would emerge focused specifically on multiverse cosmology. New funding agencies might be created. Educational curricula would require teaching students about the multiverse framework from early physics courses onward. But here's where it becomes complicated. How would scientists study the multiverse? By definition, other universes in the multiverse are causally disconnected from ours. We cannot observe them directly. we cannot conduct experiments in them. The evidence for the multiverse must be indirect through implications for our observable universe that can be tested. This requirement creates a methodological crisis in science. The scientific method has always relied on observation and experiment, but multiverse physics is, in some formulations, fundamentally untestable. How do we maintain the rigor of science when we're studying a framework that explicitly places most of reality beyond observational reach? Some physicists argue this is acceptable, that theoretical coherence and internal mathematical consistency can substitute for direct observation when studying macro-level frameworks. Others argue this abandons the core principle of empirical science. This conflict would likely produce a schism in the physics community. One faction would embrace multiverse cosmology as the best available framework, even acknowledging its inherent untestability. Another faction would resist, arguing that unfalsifiable theories, however elegant, are not science but speculation. The implications extend beyond the physics community. Religious institutions would face a profound reorientation. Many theological frameworks depend on the universe being unique, created by divine action. If the universe is one among infinite multiverses, all arising from some impersonal quantum process, the argument for divine creation becomes more attenuated. Some religions would adapt, reinterpreting theology in multiverse terms. Others would resist, viewing the multiverse framework as incompatible with belief. This would likely produce what we might call cosmological anxiety, a sense of meaninglessness arising from the perception that our universe is insignificant, that our existence is accident, that consciousness and meaning are cosmic irrelevancies. Historically, similar shifts have produced lasting psychological impacts. When Galileo displaced the Earth from the center of the cosmos, it took centuries for humanity to psychologically adjust. When Darwin showed humans were evolved from animals, social resistance was profound. The multiverse would represent a similar displacement of cosmic significance. But note, this anxiety would largely be psychological, not rational. Intellectually, we could recognize that existing in an infinite multiverse doesn't diminish the significance of our universe or our lives within it. Psychologically, the sense of cosmic insignificance would be real for many people. Governments would face unexpected questions. Should funding be diverted to multiverse research if the multiverse is, by definition, largely beyond observation? Should science curriculum include unfalsifiable theories? What is the value of pursuing knowledge we can never access? These aren't trivial questions. They would be debated by legislatures, by educational boards, by science foundations. The answers would shape which research directions receive funding, which careers seem valuable, which questions seem worth asking. There would also be implications for artificial intelligence and computation. If the multiverse framework is correct, one possible extension is the idea of simulation theory, that universes might be computationally simulated within more fundamental mathematical structures. If simulation theory were entertained seriously, it would raise unprecedented questions. Are we in a simulation? If so, what ethical obligations do we have toward entities that might be simulating us? If we eventually create superintelligent AI systems, might they be simulations of entities from higher universes studying us? These questions are currently relegated to philosophy and science fiction. But if the multiverse framework became dominant, they would migrate into legitimate scientific discourse with funding allocated to serious investigation. The general public would likely respond with a mixture of fascination and existential distress. The multiverse concept is intuitively appealing. It explains fine-tuning, removes the need for divine creation, suggests infinite possibility, but it's also disorienting. If every possible outcome occurs somewhere in the multiverse, does free will mean anything? Do choices matter? Popular media would absorb and distort these ideas. Movies would feature characters traversing to alternate universes. Television shows would explore multiverse-based premises. Books would engage with the philosophical implications. But in the process, the ideas would be simplified, romanticized, and often misrepresented. The dialogue between scientists, theologians, artists, and the public would intensify. Philosophical conferences would burgeon. New academic disciplines might emerge focused on the implications of multiverse cosmology. There would also be a potential crisis of scientific authority. If physicists are proposing frameworks that are inherently untestable, if they're asking questions that cannot be answered through experiment, the public's perception of science might shift. Is physics still a science if its cutting edge is indistinguishable from philosophy? This could fuel anti-science sentiment. Populations skeptical of scientific authority might argue, if physicists can't test their theories, why should we trust them about vaccines, climate, public health? The boundary between science and speculation would become contested territory. Scientists would argue they're exploring a coherent framework to its logical conclusions. Critics would argue they're engaging in untestable speculation while claiming scientific authority. But perhaps most profoundly, confirmation of the multiverse would force a reckoning with the limits of knowledge itself. For centuries, science operated under the assumption that, given sufficient time and resources, humanity could understand all of reality. The laws governing the universe, once understood, would be final, reducible to fundamental equations. Complete, the multiverse framework suggests otherwise. It suggests that the vast majority of reality is fundamentally beyond observational access, that our knowledge has hard boundaries, not because we haven't investigated enough, but because causality itself prevents investigation beyond those boundaries. This would be psychologically transformative. Humanity would have to accept that there are questions we can contemplate but never definitively answer. Mysteries we can model mathematically but never directly observe. A reality whose totality forever exceeds our grasp. In a strange way, this would be humbling and liberating simultaneously. Humbling because it demonstrates the ultimate limits of human knowledge. Liberating because it removes the burden of expecting science to eventually explain everything. We could accept that some questions are inherently beyond human capacity to answer. Okay? And that's not a failure, it's simply the nature of existence. The institutional response to confirmed multiverse physics would thus ripple through society in unexpected ways, transforming not just scientific practice, but religious thought, philosophical discourse, education, and the public's relationship with knowledge itself. We've explored speculative cosmology at considerable length. Now we need to address something critical. How do we maintain intellectual integrity while exploring ideas we cannot test? This is the central tension in contemporary theoretical physics. On one hand, theoretical exploration at the boundaries of knowledge is essential. Without speculative frameworks, without willingness to ask what if, physics stagnates. General relativity, quantum mechanics, and the Standard Model all began as speculative ideas that seemed to violate common sense. But through mathematical rigor and eventual experimental validation, they transformed from speculation to established science. On the other hand, there's a real risk of drifting into unfalsifiable speculation. The philosopher Karl Popper argued that for a statement to be scientific, it must be falsifiable. There must be a conceivable observation that would prove it wrong. By this standard, aspects of multiverse cosmology might not be science at all, but rather philosophical speculation masquerading as physics. The tension is legitimate, and it requires careful intellectual navigation. The scientific community addresses this through peer review, published debate, and replication attempts. When a theoretical physicist proposes a framework like eternal inflation or the multiverse, the community subjects it to scrutiny. Other physicists look for logical inconsistencies, gaps in the mathematical reasoning, conflicts with observations. This process doesn't guarantee correctness, but it prevents purely arbitrary speculation from being accepted as legitimate science. But we should be honest about the limits of this process. Peer review is excellent at catching errors and ensuring mathematical rigor. It's less effective at determining which speculative frameworks are likely to be correct. When we're far from observational boundaries, evaluation becomes increasingly about judgment and intuition. This is why intellectual honesty about uncertainty is crucial. When physicists discuss pre-Big Bang frameworks, they should be clear. This is a speculation grounded in real mathematics and consistent with current observations. But it remains fundamentally uncertain. We cannot test it with current technology and may never be able to test it. This honesty is often missing from popular communication, okay? Scientists are incentivized to present their work as important and likely correct. Funding agencies favor researchers whose work produces positive results. Dramatic claims generate media attention and prestige. There's institutional pressure toward overclaimed certainty. But whenever we find ourselves wondering about unknowable things, this overclaimed certainty becomes especially dangerous. It undermines public trust when speculative claims are presented as fact and later understanding shifts. It contributes to the erosion of scientific authority when the public realizes they've been sold uncertainty as certainty. So what's the right balance? How do we remain open to new ideas while maintaining skepticism? Several principles help. First, distinguish clearly between different epistemic levels. Observable fact: the universe expands. The CMB exists is different from established theory. The Big Bang theory explains these observations. Established theory is different from speculative framework. The multiverse might explain physical constants. Speculative framework is different from pure speculation. The universe might be conscious. When communicating science, these distinctions matter. Most people don't require this precision in casual conversation, but when making significant claims, clarity about what we know with high confidence versus what remains speculative is essential. Second, favor parsimony. When multiple frameworks explain observations equally well, prefer the simpler one. Eternal inflation explains fine-tuning elegantly through the multiverse, but so does the anthropic argument without needing infinite universes. Both have merit, but the simpler approach is preferable unless the more complex one makes predictions the simpler one doesn't. This principle, Occam's razor, has limits some of the most successful physics. Quantum mechanics, general relativity are mathematically complex, but simplicity is still a valuable guiding principle when complexity offers no additional explanatory power. Third, seek testability. Even for frameworks far from observational reach, ask, what predictions does this framework make that could, in principle, be tested? The multiverse framework predicts certain signatures in the CMB. Eternal inflation predicts specific patterns in how structure evolved in the early universe. Even if we can't test these predictions now, frameworks that make concrete predictions are preferable to those that make none. Fourth, maintain epistemic humility. Recognize that our current frameworks might be fundamentally wrong. In the history of physics, each generation believed it had discovered the true laws of nature. Newton was sure he had it right. So was every physicist before Einstein. So was every physicist before quantum mechanics. We're almost certainly wrong about fundamental aspects of reality. Humility about this likelihood should temper our certainty about any framework. Fifth, separate the map from the territory. Mathematical elegance is not evidence of truth. A framework can be internally consistent, philosophically satisfying, and still wrong about reality. The fact that we can mathematically describe a concept doesn't mean that concept has physical reality. Sixth, allow for different levels of engagement. Not every physicist needs to work on multiverse cosmology. It's appropriate for some researchers to pursue cutting-edge speculative work. It's equally appropriate for others to focus on empirically testable frameworks. Both approaches serve science. One pushes boundaries, the other grounds work in observation. The balance between skepticism and openness isn't a fixed point. It's a dynamic process. We should be skeptical of unfalsifiable claims while remaining open to frameworks that might eventually become testable. We should be humble about our current understanding while confident in the scientific method as a means of refining that understanding. In the specific case of pre-Big Bang physics, we can maintain this balance by acknowledging that multiple frameworks exist and may not be mutually exclusive. Some could be right. Most will probably be wrong. All contribute to our understanding of the landscape of possibilities. Continuing to pursue empirical research that constrains these frameworks. Even if we can't test pre-Big Bang physics directly, observations of the early universe can eliminate some frameworks and support others. Engaging seriously with philosophical implications without claiming they're established facts. We can explore what it means for the universe to emerge from the multiverse without claiming we know this is true. supporting both speculative theoretical work and empirical observation, recognizing they serve complementary roles. Most importantly, remaining honest that we don't know. The pre-Big Bang realm might be forever beyond our grasp. We might be asking the wrong questions. We might lack the conceptual frameworks even to formulate correct questions. Honesty isn't a weakness in science. It's essential to scientific integrity. Before we move toward resolution, let's expand our perspective to truly cosmic scales. Because understanding pre-Big Bang physics requires understanding how vanishingly small our knowledge is relative to the full scope of existence. The observable universe, the region of space from which light has had time to reach us since the Big Bang, spans 93 billion light-years. A light-year is the distance light travels in 1 year at 186,000 miles per second. That's about 6 trillion miles. So the observable universe is 93 billion times 6 trillion miles across. The number is so large, it loses meaning to the human mind. Within this volume, there are roughly 200 billion galaxies. Each galaxy contains roughly 200 billion stars. That's 40,000. That's 40 sextillion stars. 40 sextillion stars. Our sun is one of them. Utterly ordinary, utterly unremarkable. Around our sun orbits Earth. On Earth, in a specific location, consciousness emerged somehow. Through processes we're still struggling to understand, matter organized itself into configurations capable of thinking, wondering, asking questions about their origins. That consciousness looks upward and wonders, where did it all come from? In the grand scheme of cosmic time, consciousness has existed for an infinitesimal moment. The universe has been expanding for 13.8 billion years. Galaxies have been forming and evolving for 12 billion years. Our solar system has existed for 4.6 billion years. Life on Earth has existed for 3.8 billion years. Complex life for 600 million years. Consciousness for maybe 100,000 years. Modern science for 400 years. Physics as we know it for 150 years. Humanity is younger than a mayfly relative to cosmic time. Yet in this infinitesimal flash of consciousness, we've unraveled the mysteries of atoms, the structure of space-time, the behavior of quantum mechanics. We've built instruments sensitive enough to detect the faint afterglow of the Big Bang itself, imprinted with information about the universe's first moments. We've developed mathematical frameworks powerful enough to describe black holes, the early universe, the behavior of matter at temperatures and densities beyond anything in nature today. This is remarkable, but it also provides perspective. The universe is at least 200 times larger in space than our observable horizon. Whenever we could travel infinitely fast, it would take 200 times the age of the universe to cross from our location to the edge of the observable universe. Beyond that lies space we cannot reach because the universe is expanding faster than light could travel. And beyond that, if the multiverse is real, lie infinite other universes with potentially different physics. The fraction of existence we can access, let alone understand, is vanishingly small. We are literally studying one bubble in an infinite foam through a window the size of a hair, for a duration that registers as a quantum fluctuation on cosmic scales. What could we possibly hope to know about pre-Big Bang physics given this disproportion? And yet, here's the profound truth: we keep trying. Despite the cosmic insignificance of our perspective, despite the ultimate loneliness of consciousness in a vast universe, we continue asking questions. We continue building theories. We continue exploring the boundaries of what can be understood. Physicist Carl Sagan called Earth a pale blue dot, an unremarkable speck orbiting an ordinary star in an ordinary galaxy. When Voyager 1 took that photograph from 3.7 billion miles away, and Earth appeared as a pixel barely visible against the cosmic background, it produced what some call the overview effect, a perspective-shifting realization of the insignificance of our planet and our species. But here's what that realization reveals. Consciousness might be rare. Consciousness might be precious. A universe that, for 13.8 billion years, expanded without any conscious being to observe it, suddenly produces observers, suddenly develops the capacity for self-reflection, suddenly becomes aware of itself. From this perspective, the question what came before the Big Bang isn't a sign of arrogance, it's a sign of the deepest courtesy the universe has ever shown itself. We, as representatives of matter organized into awareness, asking the matter around us how it came to be. The universe inquiring into its own origins. This is why scientists continue to probe pre-Big Bang physics despite its fundamental elusiveness. Not because we expect to ever definitively answer the question, but because the asking itself is part of what consciousness is. Curiosity is the fundamental signature of mind. Doubt, questioning, wondering, these are the things that separate conscious systems from mere physics. The cosmic scale perspective also reveals something about pre-Big Bang physics specifically. If our universe is one bubble in an infinite multiverse, then what we call the universe is radically less significant than we've imagined. But what we call consciousness becomes more significant. In eternal inflation, universes are constantly being created. Most are sterile. Some, by pure chance, have the right physics to form galaxies, stars, chemistry, life. Of those, fewer still produce consciousness. We are in one of the rare universes where consciousness emerged. And consciousness is, as far as we know, the rarest structure that matter can form. From this perspective, we're not studying the universe. We're not trying to understand the multiverse. We're recognizing that consciousness and the universe are engaged in a cosmic conversation. The universe produced us. We're now investigating the universe. The universe, through us, is becoming aware of itself. In this light humbling and elevating simultaneously pre-Big Bang cosmology becomes something more than academic physics. It becomes the universe's attempt to understand its own existence. An effort of unprecedented sophistication, reaching backward towards something that might be forever beyond grasp, asking questions that might be inherently unanswerable, and that reaching, that asking, that ceaseless curiosity that is perhaps the most profound truth about consciousness. We can know almost nothing about pre-Big Bang physics. We can spend careers on questions unlikely to be answered in our lifetimes. We can embrace speculation that might ultimately be meaningless. We can stand on a pale blue dot in a small galaxy, in an ordinary corner of the universe, and look backward toward infinity and ask, where did it all come from? And the asking itself, the yearning itself, the refusal to accept we cannot know. As an answer, when so many answers remain possible, this is what makes consciousness matter in a universe vastly larger than any individual consciousness could comprehend. This is the cosmic perspective that pre-Big Bang cosmology provides. Not answers, but a framework for meaningful questions. We've journeyed through speculation into the darkest regions of pre-Big Bang physics. Now, let's shift our perspective towards something more hopeful. The remarkable achievements of modern cosmology and the collaborative, international effort that makes cosmological discovery possible. Despite all the uncertainty surrounding pre-Big Bang physics, our understanding of the universe has advanced at an astounding pace. In just the last 30 years, we've gone from debating the age of the universe to measuring it to within 100 million years. We've gone from uncertain about whether galaxies beyond our Milky Way existed to mapping hundreds of billions of galaxies. We've gone from theoretical speculation about black holes to actually observing and photographing them. This progress should fill us with hope about what human cooperation and scientific method can achieve. Consider the Cosmic Microwave Background Research Program. It began with Penzias and Wilson's accidental discovery in 1965. Today, international teams use satellites like Planck ground-based telescopes in Antarctica and balloons carrying instruments above most of Earth's atmosphere to map the CMB with extraordinary precision. The data shows radiation patterns consistent with predictions from inflation theory. Those patterns reveal the geometry of the universe, the age of the universe, the composition of the universe. This is international collaboration on an unprecedented scale. Russian physicists work alongside American colleagues. Chinese institutions contribute. European organizations participate. The data is released publicly so that thousands of researchers across the globe can analyze it. Similarly, the study of distant galaxies and cosmic expansion involves telescope networks across multiple continents. The European Southern Observatory operates facilities in the Chilean Andes. NASA's Hubble Space Telescope orbits Earth. The recently launched James Webb Space Telescope, a collaboration between NASA, the European Space Agency, and the Canadian Space Agency, is revealing galaxies formed only a few 100 million years after the Big Bang. These achievements don't directly answer pre-Big Bang questions, but they demonstrate something crucial. When humanity coordinates around shared curiosity, remarkable things become possible. We can measure what seemed unmeasurable. We can observe what seemed unobservable. This collaborative approach extends to theoretical work. The development of quantum field theory, the Standard Model, string theory, and quantum cosmology involved researchers from dozens of countries, competing and collaborating, building on each other's work, pushing toward deeper understanding. What's remarkable is that this cooperation has persisted through geopolitical tensions, economic challenges, and disputes over scientific methodology. The Cold War did not prevent Soviet and American physicists from collaborating on fundamental physics. Economic disparities don't prevent researchers in developing nations from contributing to cutting-edge theoretical work. There's something profound about this. Despite our capacity for conflict, despite the divisions that separate human societies, there exists a shared human drive to understand reality, a recognition that this drive transcends national borders, economic systems, religious beliefs. In this sense, the international scientific community working on cosmology represents humanity at its best. Not destroying each other over resources, not fighting over ideology, but standing together, looking upward at the stars and asking, what does the universe tell us about itself? The data emerging from this collaborative effort is transformative. We now have more information about the early universe than anyone would have predicted possible 50 years ago. We're measuring parameters that determine cosmic fate. We're discovering that 95% of the universe's energy density is unknown dark matter and dark energy populations that could reshape our understanding if we ever learn their true nature. This is where hope lies, not in certainty, but in the ongoing process of discovery. We don't have final answers about pre-Big Bang physics. Cool, but we're getting better at asking precise questions. We're designing experiments that can test some of the frameworks we've discussed. We're developing new technologies that reveal aspects of reality previously hidden. The James Webb Space Telescope is currently observing galaxies so distant that we're seeing them as they were 13.5 billion years ago, 300 million years after the Big Bang. As these observations pour in, they'll constrain the parameters of inflation. They'll test whether the early universe matches theoretical predictions. They won't directly answer pre-Big Bang questions, but they'll refine our understanding of the boundary itself. Future gravitational wave observatories might detect signatures from the early universe. Primordial gravitational waves, ripples in spacetime created by the Big Bang itself, carry information about the conditions. Immediately after the Big Bang, if detected with sufficient precision, they could test quantum effects in the early universe in ways we currently can't. And there are proposals for even more ambitious projects. New observatories to detect the faint signals from the very early universe. Telescopes sensitive enough to detect individual cosmic microwave background photons. Instruments designed to search for evidence of other universes in the structures we observe around us. None of these will definitively answer what came before the Big Bang, but they'll constrain the possibilities. They'll eliminate some theories and support others. They'll gradually refine our understanding toward whatever truth lies at the foundation of existence. This is the nature of scientific progress, not dramatic revelation, but incremental refinement. A process that never reaches completion because reality is always more complex than our latest theory, but a process that moves us steadily toward better understanding, deeper insight, greater connection with the fundamental nature of existence. What gives me hope is not the expectation of definitive answers. It's the fact that humanity, for all its flaws, for all the suffering and violence we inflict on each other, still maintains this commitment to understanding, still funds observatories, still trains young scientists, still publishes papers in peer-reviewed journals, still debates difficult ideas with intellectual honesty. The collaborative international effort to understand cosmology represents something transcendent. It's the best of what consciousness can do, not just ask questions, but pursue answers collectively, sharing data openly, building on each other's insights, moving toward deeper understanding. That collaborative effort has already accomplished remarkable things. It's already pushed back the boundary between known and unknown in ways that would astonish scientists from just a generation ago. And it will continue even when the questions are ultimately unanswerable, because the asking itself has value. There's hope in that. Not the hope of finding final answers about pre-Big Bang physics, but the hope that human cooperation in pursuit of understanding continues, that we remain committed to asking the deepest questions, that consciousness continues to reach toward the unknowable. Before we move toward conclusions, let's deepen our understanding of quantum cosmology, the field that underlies much of pre-Big Bang speculation. This is complex material, but understanding it empowers you with genuine insight into how physicists approach the most extreme questions. Classical cosmology uses Einstein's general relativity to describe the universe. General relativity is a deterministic theory. Given initial conditions, the equations determine exactly what happens next. The universe evolves according to mathematical laws. But general relativity breaks down at the Big Bang, where the density becomes infinite. To address this, physicists turn to quantum mechanics, the other fundamental pillar of modern physics. Quantum mechanics describes systems at tiny scales. At the quantum level, determinism breaks down. Instead, we have probabilities. Can't know both a particle's position and momentum precisely. Particles exist in superposition multiple states simultaneously until measured. Quantum cosmology attempts to apply quantum mechanics to the entire universe. Instead of the universe following one definite trajectory, it exists in a superposition of all possible trajectories. Each trajectory is weighted by a probability amplitude determined by quantum mechanics. This immediately raises philosophical questions. What does it mean for the entire universe to be in superposition? What constitutes a measurement of the universe when there's nothing outside the universe to do the measuring? Who observes the universe into a definite state? These questions have no consensus answers. This is why quantum cosmology remains so speculative. One approach, the Wheeler-DeWitt equation, named after Bryce DeWitt and John Wheeler, who developed it. This equation describes how the quantum state of the universe evolves. But unlike the Schrödinger equation in standard quantum mechanics, which shows how probability waves evolve through time, the Wheeler-DeWitt equation doesn't include time explicitly. This is profound because it suggests time isn't fundamental. Time might emerge as a property of certain quantum states rather than being a fundamental background. The equation doesn't ask how does the universe evolve through time. It asks what is the quantum state of the universe. The solution to the Wheeler-DeWitt equation is the wave function of the universa mathematical object that encodes all possible configurations the universe could have, weighted by their quantum probabilities. Now, to answer, what about before the Big Bang? Quantum cosmologists ask, What does this wave function predict about boundary conditions? One answer, from Hartle and Hawking, is the no-boundary condition. They proposed solving the Wheeler-DeWitt equation with boundary conditions that eliminate the need for a before, the universe's history. In their formulation is a closed, four-dimensional surface with no boundary analogous to the surface of a sphere. Another answer, from Alexander Vilenkin, is the tunneling proposal. Vilenkin argued the universe could have tunneled into existence from a state of non-existence. In quantum mechanics, tunneling allows particles to pass through barriers they couldn't cross classically. Keane proposed the universe might tunnel from nothing into a state of existence without requiring any external cause. To understand tunneling, imagine a ball on top of a hill. Classically, without enough energy, it can't roll over to the other side. Quantum mechanically, the ball has a probability of tunneling through the hill and appearing on the other side. The probability depends on the height and width of the barrier. If the entire universe can tunnel, it might tunnel from no universe to universe. This would mean the universe creates itself through quantum mechanics, no external cause needed. But here's where the mathematics becomes genuinely challenging. How do you calculate the tunneling amplitude for something that has no initial existence? What's the barrier height if there's nothing initially to have a height? The mathematics becomes ill-defined, and quantum cosmologists disagree about how to properly formulate the problem. Then there's the eternal inflation picture, which incorporates quantum mechanics into inflation theory. In this framework, the inflated field, the field that drives inflation, evolves quantum mechanically. Quantum fluctuations cause different regions to have slightly different values of the inflated field, leading some regions to inflate longer than others, eventually spawning separate universes. This framework is testable in principle. Eternal inflation makes predictions about the pattern of density fluctuations in the CMB, predictions that can be compared against observations. What all these approaches share, they're attempting to extend quantum mechanics to the most extreme regime, the moment of cosmic origin. They're asking whether the tools that work brilliantly for describing atoms and particles can be extended to the universe itself. The challenge is profound. Quantum mechanics was developed for systems small enough to create in laboratories. We can control the initial conditions, measure the outcomes, repeat the experiment. None of this is possible for the universe. Additionally, quantum mechanics contains an element we don't fully understand: the measurement problem. What constitutes a measurement? What causes the quantum wave function to collapse into a definite state? In laboratory settings, we assume an external observer exists to measure the system. But for the universe, there's no external observer. Some physicists propose that consciousness plays a role, that the act of conscious observation collapses the universe's wave function. Others argue this is mystical nonsense, that measurement just means interaction with any system, consciousness unnecessary. Still others propose that decoherence, the interaction of quantum systems with their p-went. Their environment causes wave function collapse without needing consciousness. The debate continues, unresolved. So quantum cosmology gives us frameworks for thinking about pre-Big Bang physics, but not definitive answers. It shows us how quantum mechanics might extend to cosmic scales. but it also reveals how far we still are from a complete theory of quantum gravity. The ultimate theory, the one that correctly describes gravity at quantum scales, remains unknown. String theory, loop quantum gravity, asymptotic safety, causal set theory, multiple candidates exist, each with philosophical adherents and detractors. None has been confirmed experimentally. Until we have a confirmed theory of quantum gravity, pre-Big Bang physics will remain speculative. But the frameworks we've discussed show how contemporary physicists are wrestling with this frontier. They're not inventing fanciful myths. They're extending our best-tested physics to its limits and exploring what emerges. That's real science, even when the answers remain elusive. Where does cosmology go from here? What missions, what observations, what theoretical developments might advance our understanding of the Big Bang and pre-Big Bang physics? The next 2 decades will likely be dominated by several major initiatives. The James Webb Space Telescope, JWST, launched in 2021, is the most powerful space observatory ever built. It observes primarily in infrared, allowing it to see through dust clouds and look back in time to when the universe was young. Its mission is to observe the earliest galaxies, those formed within the first 100 to 200 million years after the Big Bang. These observations will test inflation theory predictions and constrain the initial conditions of the universe. As JWST data accumulates, we'll gain unprecedented knowledge of how galaxies formed and evolved. We'll be able to test whether the universe truly looked as inflation theory predicts. If significant deviations emerge, our understanding will have to shift. The Vera C. Rubin Observatory, formerly the Large Synoptic Survey Telescope, under construction in Chile, will map the sky repeatedly throughout the night, discovering transient objects and measuring cosmic expansion through millions of supernovae. This will refine our understanding of cosmic acceleration and test whether dark energy truly has a constant density or varies with time distinction. That carries profound implications for cosmic fate. Future gravitational wave observatories will extend our detection capabilities. The Laser Interferometer Gravitational Wave Observatory LIGO currently detects gravitational waves from merging black holes and neutron stars. Future detectors with longer baselines, potentially in space, might detect gravitational waves from the early universe. Waves created by the Big Bang itself. Primordial gravitational waves are a prediction of inflation theory. If detected with sufficient precision, they would provide direct evidence about the conditions during inflation, constraining the theories we've discussed. Additionally, the cosmic microwave background will continue to be observed with increasing sensitivity. Planck's satellite data is still being analyzed, and future CMB observatories will map the background radiation with unprecedented detail. Higher sensitivity might reveal subtle signatures. Currently, invisible potential evidence of collisions with other universes as predicted by some multiverse models, or signatures of exotic processes in the early universe. On the theoretical front, the search for quantum gravity continues to intensify. String theory has produced decades of research, generating beautiful mathematical structures, but limited experimental predictions. Loop quantum gravity offers an alternative approach, quantizing spacetime itself into discrete units. Asymptotic safety proposes that gravity might have special mathematical properties that allow it to be renormalizable without infinity's quantum scales. Each of these frameworks suggests different pre-Big Bang physics. In string theory, the universe might be one of 10,500 possibilities in the string landscape. In loop quantum gravity, the Big Bang might be preceded by a big bounce-a-contracting universe that rebounds and becomes our expanding universe. In asymptotic safety, the Big Bang might have special mathematical properties that eliminate the need for initial conditions. Future theoretical breakthroughs might come from unexpected directions. New mathematical structures might be discovered that change how we think about spacetime. New insights from machine learning applied to theoretical physics might reveal patterns humans missed. New observations might falsify existing theories, forcing re-examination of foundations. The search for dark matter and dark energy will also continue. These mysterious components make up 95% of the universe's energy density. Understanding their nature would likely require physics beyond the standard model, potentially providing clues to pre-Big Bang physics. Some theories of quantum gravity predict specific behaviors for dark matter and dark energy. Future observations might confirm or falsify these predictions. In the next 50 years, we might answer some fundamental questions. Did inflation actually occur? Is the multiverse real? What is the nature of dark matter and dark energy? Can we detect primordial gravitational waves from the Big Bang? Is space-time truly continuous or discrete at the Planck scale? But some questions might remain permanently beyond our reach. What happened before the Big Bang, if that phrase has meaning? Why do the fundamental constants have their observed values? Why is there something rather than nothing? What is the ultimate foundation of physical law? These aren't questions science can necessarily answer through observation alone. They might require philosophical insight, mathematical revelation, or conceptual innovations we can't yet imagine. Yet the pursuit continues. Future scientists will peer deeper into the early universe. They'll develop more sophisticated theories. They'll ask better questions. And through this process, not through final answers, but through the ongoing refinement of understanding consciousness, will continue its conversation with the cosmos. What's exciting about the future of cosmology is not the expectation of definitive answers about pre-Big Bang physics. It's the certainty that the questions will become more precise, the observations more sensitive, the theories more sophisticated. The boundary between known and unknown will shift, even if it never disappears. In 50 years, our understanding of the Big Bang will likely be radically different from today. The way today's understanding differs from 50 years ago. And in 100 years, physicists will look back at our current speculations and wonder how we could have gotten so much wrong. But they'll also, hopefully, recognize that we did our best with the tools available, that we pursued deep questions with intellectual honesty, that we maintained both rigor and wonder, skepticism and openness. That is the future of cosmology, not final answers, but an ongoing evolution of understanding, an endless frontier of discovery. We've journeyed tonight through the deepest mysteries of cosmology, from the observable Big Bang backward into the speculative realm of pre-universal physics. We've explored frameworks, some rigorous, some exotic, for thinking about what might have preceded time itself. As we conclude this exploration, it's time for reflection. Let's return to where we began, with a provocative question. What if the truth about nothing before the Big Bang is precisely that nothing is the most meaningful word in cosmology? Nothing as the absence of something. Nothing as empty space waiting to be filled. But nothing as the ground state of existence, the state that precedes all distinction between being and non-being, between existence and non-existence. If the mathematical universe hypothesis is correct, if all possible realities exist equally in Platonic space, then before any specific universe, before our Big Bang, there was no particular reality. There was only the infinite landscape of all possibilities, undifferentiated and eternal. The Big Bang, then, wasn't creation, it was selection. One specific universe crystallizing from the infinite potential. One set of laws emerging from infinite possibility. One reality becoming conscious of itself through the emergence of observers. We are the universe becoming aware. We are the cosmos asking itself where it came from. This isn't mysticism. This isn't religion. It's the logical extension of our best physics, extended to its ultimate conclusion. When we ask what came before the Big Bang, we're asking a question that assumes a distinction between before and after, between cause and effect, between one moment and another. But time is part of the universe. Time emerged with the Big Bang. To ask what happened before time is to ask a question that violates the fundamental structure of reality. It's a question that can only be asked because consciousness, having emerged within this universe, has developed the capacity to imagine other possibilities. We can imagine time flowing backward. We can imagine an earlier moment. We can conceive of before, even though before is physically meaningless. This capacity for imagining the impossible, this is what makes consciousness remarkable. It's not just that we observe the universe, it's that we imagine beyond it, that we ask questions reality might not permit answers to, wire about things we can never know, and that wondering itself, that refusal to accept the unknowable as the end of inquiry, that is the deepest truth about consciousness. So what came before the Big Bang? So the honest answer is, we don't know, and we might not be able to know. The physical boundary of the Big Bang might be absolute. The question might be inherently unanswerable. Time might not extend backward before it began, but also the universe might be one bubble in an infinite multiverse. The Big Bang might have been preceded by previous universes or by an infinite quantum foam. Time might be emergent, constructed from more fundamental entities. Consciousness might have reached backward through quantum entanglement to influence the initial conditions of the universe. The universe might be a self-creating loop. Reality might be a mathematical structure, or a simulation, or something we lack the conceptual framework even to imagine. All of these remain possible. All remain uncertain. All remain genuinely mysterious. And that's what I want to leave you with. Not an answer, but an appreciation for the profound strangeness of existence, the fact that anything at all exists, that the existence that does occur follows elegant mathematical laws. Consciousness emerges in this existence. That consciousness can ask the deepest questions. In the grand scope of cosmic time and space, you are infinitesimal. Your individual existence lasts perhaps a century. The universe will continue for trillions of years after you're gone. The multiverse, if it exists, will continue eternally beyond that. Yet right now, in this moment, you're thinking about cosmic origins. You're contemplating what came before time itself. You're engaging in what might be the universe's deepest form of self-knowledge. That's extraordinary. Not because the answer matters, the answer might be unknowable, but because the asking matters, because consciousness, having emerged in this universe, insists on understanding itself. Because we look at the stars and wonder. The hidden truth about nothing before the Big Bang might be that there is no truth too. Discover only an eternal mystery that consciousness will forever reach toward. And in that reaching, in that yearning toward the unknowable, consciousness becomes what it most fundamentally is. So I want to thank you for spending this time with me, exploring the boundaries of what we know, for being willing to venture into speculation, into uncertainty, into the genuine mysteries that remain at the heart of physics, for caring about these questions, because cosmology ultimately isn't about answers. It's about the conversation between consciousness and the cosmos. It's about the fact that matter, arranged in just the right way, can become aware of itself, can ask where it came from, can reach toward the infinite. The universe is stranger and more wonderful than our equations capture. It might be infinite. It might be one of infinite multiverses. It might be conscious, or it might be unconscious, but producing consciousness. It might have had a beginning, or it might be eternal. It might be governed by mathematics, or by something beyond mathematics that we have no words for. We don't know, and perhaps we never will. But the asking, the continuous, relentless, deeply human asking, that is what makes us part of this universe, rather than mere objects within it. That is what makes consciousness real. So the next time you look up at the stars, remember, you're not just observing distant suns. You're participating in the universe's attempt to know itself. You're a temporary arrangement of matter that has achieved consciousness and is using that consciousness to investigate the ground of its own being. That's what we are. That's what this conversation tonight represents. The universe before the Big Bang remains unknowable, but the universe after the Big Bang, our universe continues to reveal its wonders to those willing to ask questions. Thank you for asking tonight. Thank you for wondering. Thank you for caring about these mysteries. Good night, and may your wondering continue forever.